Hi guys, welcome to my channel. I'm Navya. So today we will be solving Leetcode question number 1284, minimum number of flips to convert binary matrix to a zero matrix. So let's see what the question is along with some given examples. So the question says that we are given an m cross n binary matrix. So by binary matrix, that means that you can have either 1 or 0 present in the matrix. So in one step, you can choose one cell and flip it. So that means when you flip it, it means that if there is a 0, you make it 1, and if there is a 1, you make it 0. So you flip that cell, and also you're going to flip all the 4 neighbors of it, right? So if they exist. So basically, we need to do this flipping till the point where we get all the matrix elements as 0. So this is called being a zero matrix. So we have to convert it in the minimum number of possible steps that will be required to make this given matrix to a zero matrix. And there can be cases where we cannot convert it. So in that case, we need to return -1. So let's see by walking through this example that we have given as a test case. So we are given this matrix. I have drawn this matrix over here so that it can be used for a clear explanation. So this is the given matrix, and now let's see that what are the type of operations that we can do to make it reach the zero matrix, right? So you can see this matrix over here. So I have made a 2 cross 2 matrix, and I have labeled the indexes of the row and column. So if I say that you choose this cell and you say that I want to flip this element present in this cell, right? So since it's a 0, flipping it will mean to make it 1. So if you flip this bit, right, you can just flip only one bit. So I choose to flip this bit and I make it 1, right? So if I am flipping this, I also need to flip all its possible 4 neighbors. So in this case, we have only 2 neighbors possible because the up and left neighbor is not present because it's the starting cell. So there are only right and down neighbors, right? So we need to flip these two also. So we also have to make them, sorry, it will be 1 because 0 is present here, so we'll write 1 here, and 0 is also here, so we have to flip it to make it 1. But we don't have to do anything with the rest of any element, so this one will be the same one, right? So this is the new state that we found by flipping this cell from 0 to 1, so its neighbors are also flipped. So this is one possible case, one possible state that can be achieved while we are flipping bits. So this is just to show you how the flipping is actually happening, right? So let's take another case. If I say that I want to flip this bit, and the state of the matrix previously was this, right? So if I want to flip this, so first I'll flip it by making 1 to 0, and I'll make it I'll also flip its neighbors. So 0 will be flipped to 1, and here also 0 will be flipped to 1, but this 0 will remain the same because it's not the neighbor of this cell, right? So now if you see that from this state that we had previously, we are able to reach to two different states. If we flip, suppose if we chose to flip two cells, then we are able to reach to two different states. So similarly, if we had flipped the other two cells like this one and this one, we would have got two more states. So it's like that in a matrix, you from one state, you can have around m cross n states. So basically m is the number of rows and n is the number of columns. So you can have uh, up to m cross n distinct states that you can achieve by flipping each of the bit, right? So if I talk about this, since it's 2 cross 2, so if I flip every element in it, I have just shown 2. If I flip these elements also, both of them, so I'll achieve two different states. So total number of states will be m cross n, that is 2, right? So from one previous state, I'm able to achieve 4 different states. So using these states also, I can get many other different states, right? Following the similar ideology of flipping the bits. So in this way, we have to tell that what would be the number of steps. So basically it's like the number of states that you have to go through to reach a matrix where all the elements are zero. So we have to do this. So the algorithm for solving this would be a simple BFS, right? It's very like it's something like you can also think about it, because we are asked to tell the minimum number of steps to achieve a possible state from a given state, right? So the basic very simple kind of algorithm that could come into our minds is BFS, because it gets very easy to traverse level by level. So by that you will be able to actually count what is the minimum number of steps that you will be needing to achieve the zero, to reach the zero matrix. So I said that we'll be using BFS, but we also need to think about that we have a matrix over here, right? So and we also need to flip the bits of it, and we have to create a lot of states, right? So how are we going to handle that matrix in case of BFS? Because we have actually not seen many such problems where we are needed to handle a matrix while doing BFS, right? So my approach here would be that you don't need to handle a matrix while you are applying BFS in your code. You just have to think of like a smart way to deal with this matrix. So my way was to actually convert this matrix into a string of m cross n length. So if you see this matrix, I have written this 0, 1, 2, 3 over here just to show you this fact that you don't need to handle the matrix in every stage of BFS. You need to you just can convert it into a string. So let's start from here. You have this initial matrix, right? So now I can convert this matrix into this string 0, 0, 0 and 1. So this is my initial string given to me. So I'll be traversing row wise and then converting it into a string. But you should also know that every time the length of the string is going to be m cross n, that is from the index 0 to the index 3 in this case, because m cross n here will be 4, so the indexing will be from 0 to 3. So in this similar way, you can deal it with in the form of a string, and that will make your work very easier to handle. So I hope that you must have understood this smart trick that I'm going to use here. But a question might come to your mind that how are we actually going to flip the bits? Like it's like you can flip the bit of that particular index, but how are you going to identify that what are its neighbors that need to be flipped according to the matrix position of the elements, right? Because this is something we have converted into a linear fashion, and this is a 2D fashion, right? So we need to flip the elements based on the position they are actually in the matrix, right? So for this element, the neighbors will be this and this one. So we have to find actually that what is their position in the given string, because when it is being converted into a string, then they need not be adjacent, right? So we need to figure out what are the actual neighbors that need to be flipped. So I hope that it's clear. So firstly, I would like to write that how are we actually going to convert this matrix into a string. So it's a bit like it's a kind of a formula just to tell you how I actually derived this thinking. So if I say that I converted this matrix into a string which is of length m cross n, right? So there will be indexes from 0 to m cross n minus 1 in the string. So for every index, so new index can be represented as j plus I star n. So by j plus I star n, what I mean is, so this is a formula that I derived myself while I was trying to figure out that how can I convert it into a string. So this is just simple math. Even if you sit and try for just 5 to 10 minutes, you'll figure it out that how can I convert it into like in a fashion from 0 to m cross n, right? So you can see over here that we have this first element, right? So the new index for the string will have to be 0. For this element, the index will be 1. For this element, it has to be 2. And for this element, it has to be 3. That is how the string will be formed, right? So let's figure out that how did it actually came. So if you see that for this element I is 0 and j is 0, so you get 0. For this element, j is 1 and I is 0. So 0 into n is 0 and you are left with 1 only. So that's your new index for the string position of this element, right? And then in this case, the I is 1 and j is 0. So j is 0, then 1 cross n here is 2. We are given n is 2, 2 cross 2 matrix. So you have 2 here. In this case, it's 1, 1 comma 1, ij is 1, 1. So you can figure it out. It is going to be 3. So this is how, using this formula, I actually thought of converting this matrix into a string, right? So this formula is going to be very helpful for us while we are going to find the neighbors that need to be flipped. So I hope you got the part till now. So we made it a string, right? Now let's take an example of how are we going to flip this. So now you have this initial string. So by applying the concepts of BFS, you put this initial string into a queue, right? So when you pop it out, you just have one element that is this string. So now we have to, as I already mentioned, that from this string we can get 4 different possible states in this case, because we can try flipping every one of its bit, every one of its, like you can flip this 0, this 0, this 0 and this one. So there are 4 possible bits that can be flipped, right? So you can get 4 different possible states. So we'll try to do the same thing. So when you pop this string from the queue, then you try to loop over this string that you got. So you come to 0 over here. The first element is 0 and its index is 0. Now, when you see it, you only know that it's an element of a string, but you need to find its coordinate that was its original coordinates in the matrix, right? So you need to translate back now. So how do you get this element's coordinates that were there in the matrix? So for that, I already told about this formula. So if we think some mathematically, so you'll see that the index of this element is 0, and if you divide this element's index by n, so n here is 2, right? So you'll get, this will be the x coordinate, and using this formula, substituting the values in this, then you can get the value of j, that will be the y coordinate. So I'll show you how. So suppose let's say that you had this x, just a minute. Yeah, so we are on the index 0 of this string, right? So you have the index 0, as I said, you divide it by 2. So you divide it by 2 and you got it as 0, and that is going to be the x coordinate of this element in the matrix. So now how do you get the y coordinate? So now you know that my x coordinate is 0. So my new index is also 0, the new index of string. So this is 0, and then I have to find j, that will be my y, and then I have the I that I found here, that is the x, as 0, and then I am going to multiply it by 2. So you just substitute it in this formula to get the value of j back. So now you'll find that y is also 0. So now you know this is the position, 0, 0 is the position of this element in the original matrix that we had. So similarly, you can translate back the position of the elements by using this concept, right? So using just the same concept, we are going to find its neighbors also. So if this coordinate, we got its original coordinates in the matrix, right? So what we are going to do is, so we have this element, so we'll flip this first. So first I'll make this as 1, right? So I made it as 1, I flipped it. Now I need to flip its neighbors. So neighbors can only be found out only if we know its original coordinates that were there in the matrix. So now you also found out the original coordinates over here, right? So it was 0, 0. So now finding its neighbors is really very easy. You just have to go one step down, one step right, one step up, and one step left. So it is actually very easy. That's what you just have to do. So using this formula only. So now you know the I and j, right? So now you know the I and j. You just need to like do I plus 1 if you have to go to the right neighbor. You have to do I minus 1 if you have to go to the left neighbor. Similarly, j plus 1 for going down and j minus 1 for going up. So you are going to get the new index of its neighbors in the string. So you can flip it the way you flipped this element, right? So I hope you understood how are we actually going to translate the string back to the matrix to get the coordinates and then get the neighbors and then again translate it back to the string coordinate system and then flip that value to 0, right? So let's try to dry run one thing and then it will be easily understood. So I flipped this bit so it became 1 and its coordinates are 0 comma 0 that I calculated with this formula. So now I have to find its neighbors. So finding its neighbors, as I said, the formula will be this formula. So let's say I have to find its top neighbor, right? So I'll find the top neighbor. So it will be j is 0 here, right? So j is 0 here plus then the top neighbor I minus 1 if we have to find a top neighbor. So I is also 0. So 0 minus 1 will be minus 1 and n here is 2, right? So you got minus 2. But you also need to check that the index ranges should be between 0 to like it should be between 0, like it should not go out of bounds. So you need to check it should be greater than 0 and at the same time it should also meet the requirements of its row and column constraints. So make sure that it is a positive index, not a negative index. So if this happens, you have to ignore it. So we have to ignore it. That means we don't have a left neighbor, right? So now you check for a right neighbor. So applying the same formula, j will be 0 and then we need to make I plus 1 here because we are checking for the right neighbor. So I plus 1 here will be 1. 0 plus 1 is 1 and then you have 2, right? So you get 2 over here. So I actually said things wrong way that if you have to look for left and right neighbors, then you need to do plus and minus in j in y coordinate, and if you have to look for top and down neighbors, then you have to do plus and minus 1 in the x coordinate, right? So I hope that was just a mistake while speaking, but I hope that sounds good to you now. So you know, by this we are trying to find the right neighbor. Sorry, we actually incremented I plus 1. So we are finding the down neighbor. So you saw the down neighbor by incrementing I by 1. So you found the down neighbor now. So down neighbor is at index 2, right? So that is what index 2 is present here. So index 2 is this. So you are going to flip it to 1, right? So you flipped one neighbor. Now you have to see to the right neighbor. Let's see to the right neighbor. So for seeing the right neighbor, I need to increment j by 1, right? So my new index will be j has to be incremented by 1. So 0 plus 1 is going to be 1. Then you do a plus and then I was 0 originally because the coordinates of this element is 0 comma 0. So 0 into n. So it is going to be 1, right? So you found the right neighbor at index 1 in the string. So you are going to flip it to, you flipped it. And similarly, you can check for the left neighbor. It is going to be a negative number. The index is going to be a negative number. And so it is not between 0 and m cross n. So that means that it is not a valid index. So there is no left neighbor. So we are done seeing all the 4 neighbors. So we can, copy rest of the elements as the same. Sorry, it won't be a 0 here. It will be a 1 here because the last element will be copied, right? So you see this state of the matrix has been translated to the string. So it's a similar thing that we got. So this is going to be the approach that we are going to do. And you can do the BFS till you not find a string which has all the contents as 0. If you find that, then you can return the count variable that you were keeping to count the number of steps that it is taking to translate into a 0 string. So I hope that's clear now. So now let's look at the code so it will be more clear with the code. So here's the code, and let's start from the top. So we are given this function in which we are given a matrix, right? So you find the m and n of the matrix, that is the number of rows and columns. So now you start, and as I told you that convert the initial given matrix into a string. So for that I looped over all the elements, and then I used toString to convert it to a string, and then I just concatenated all the elements to form a string, so in this variable. And meanwhile, since the length of the string is going to be m cross n, so I also created a zero string which contains all the zeros of length m cross n only, so that we know this is our final state. So this zero string is going to be a final state that we have to match it with in the BFS, right? So if this string that we formed is already a zero string, that means the input was already a zero matrix given to us, then we can return zero because we won't require any steps because it's already a zero matrix, right? So then if it's not the case, then you start the actual BFS. You create a visited that we normally have in BFS, right? So it is going to be a string bool map, and then you create a queue of string. You push the initial string of the matrix that you made right now into the queue, and you mark it as visited, and you keep a variable. I have named it flips air to just count that how many transitions do we have to go through to reach the final stage that we have, that of having a zero matrix. So this is just like any other BFS problem that you would have dealt with, right? It's just the way how you handle the matrix. So now, since we need to traverse level by level so that we can find the minimum number of steps that we are going to need, so I initially take the size that was size of the queue, and then I'm going to loop it into that loop up to that much size, so that I complete levels by level. I don't mix all the levels in one, right? So before starting a level, you count increment the flips by one, and then when you come to the main part, there you pop the element and store it into a variable current, right? And then, as I said, that you are going to you have to make all possible states that you can make by flipping each and every bit of the string that we have made, right? So I have taken a variable k, and that is going to loop over all the elements. So I am going to flip every one of it, and I'm going to create a new state out of it, so that I can find that in which way I can reach the zero matrix first. So as I told you, this is the way how we are going to get the coordinates of that element that was actually the real coordinates of it in the matrix that was given to us. So I showed you how this works. So this is calculating the x and y coordinates of that element by using this formula. This I have showed you by an example. I hope you are able to recall it. And once you calculate it, so you have to flip it. So for flipping the ith bit, the bit on which you currently are, you also need to flip that. So for flipping that bit, I have XORed that particular like positions content with 1, because whenever you XOR any number with 1, like it's like you are going to, if you XOR 0 with 1, then you are going to get 1, and if you XOR 1 with 1, you're going to get 0. So in this way you are flipping the bits, right? So this fulfills our need. So I have XORed it with 1, so this is going to be flipped, right? So we flipped the ith bit. Now we need to flip its neighbors. So as I told you that for seeing the bottom neighbor, we are going to use that formula that I mentioned, and we just have to do I plus 1, because we are looking at the down like the bottom neighbor. By standing at the ith position, we are seeing at the bottom neighbor. So you do I plus 1 over here, and then you check that it is between 0 and m star n, so that it doesn't go out of bounds of the indexes of string, because the string length can be has to be of m star n. So then when you get it, you flip that bit, and similarly you do it for top, right, and left. And as I explained you with the help of an example, so you have to do this. So once you have flipped, right, so now you need to check that after flipping, So is my string equal to 0 string? So if it's true, all the contents of the string have become 0, then you return the number of flips till now. And if it's not, and if that particular state is not visited, we need to keep visited just to make track that we don't keep on looping into duplicate states that we have already visited, because that can lead us to into an infinite loop, right? So you have visited, or if this state is not visited, you push it into the queue and you make its visited as true. So this is just like any other BFS, and you have to just handle it with more care, so that it doesn't you are able to handle a proper matrix in the form of a string while doing BFS. One more thing that I would like to make a notice of, that while we are dealing with right and left, we need to keep a check of two different conditions, as I mentioned here. You can see that uh, when we created the new index, here I have said that j is not equal to n minus 1, and here I have written j is not equal to 0, but I have not written any such condition in the bottom and top cases. This is because, let me show you how I'm saying. Suppose you are on this bit, right? And you are saying that you need to find its left neighbor. So how do you find its left neighbor? As I mentioned the formula. So if you are going to the left, you need to look at j minus 1, right? Because you're going to the left. So the formula here will be, so the j here is 0. So 0 minus 1 is minus 1, plus I of this position is 1, right? And the n value is 2. So what you get as a result, you can see that 2 minus 1 is 1, so you get its left neighbor as this, but that is actually wrong. This happens because we are converting it into a string in this fashion, right? You go from here and then you go from here, so this actually has got linked. So we need to break that link, so that in actual matrix we don't see its left neighbor as this element, right? So this is wrong. Its left neighbor is not possible, and we are getting its left neighbor as this. So we have to check for that condition. So if j equals to, if we are looking for a left neighbor and the j is equal to 0, then in that case we have to avoid looking at its left neighbor, because you will get a wrong answer. So avoid looking at its left neighbor, because you can't have a left neighbor, right? And similarly, if you're standing here and you're looking for a right neighbor, you'll get its right neighbor as this element. You can calculate the same. You'll get the right as its neighbor, because we have converted it into a string in this fashion, right? So it has got linked. So that is why you need to avoid seeing its right neighbor. So that is why I have mentioned a condition where when you're looking to write, you need to make sure that j is not equal to n minus 1. So just to avoid the wrong calculation of the right and left neighbor. So that will only happen in the case when when you're on the first column and you're looking for a left neighbor, and when you're on the last column and you're looking for a right neighbor. So I hope this is understandable, and with this I'll try submitting the code, and then you can see that this code is working. And I hope this could make you understand how we made use of BFS with the help of converting a graph into a string and handling the possible states, right? So thank you guys for watching the video.